Hi. Is everyone awake? Okay, good, because we're going to learn some things. There's some math involved, so I hope we're all prepared. I'm Serkan Piantino, and I want to talk about things that we can do now, primarily with neural networks, that we could not do with computers 5 years ago. And as we mentioned, most recently, I was at Facebook, and I founded Facebook New York, and was co-director of Facebook AI research with Jan LeCun, our Facebook's AI research lab. So before we get into AI, I want to talk about something called machine learning. And machine learning is really the sort of like math basis behind all the things we're going to talk about. So it'll be useful to do a review here. First, what is machine learning? Well, let's say we have some function that we want to compute, something, but we don't really know anything about it. We have no idea what the function might look like. But what we do have is a bunch of examples of inputs and outputs to the function. And so what we want to do is learn some approximation that might fit the data we have and approximate the function. So that's sort of difficult. I have a little demo here of what this might look like. Here, this line in green is a function that we want to learn. And this line in blue is increasingly using data that it's sampling from the function, modifying itself to better approximate the function in green. And you can see it kind of jiggles around a little bit. It takes some time. But eventually, it goes from being a really poor approximation of the function in green to being actually a quite good approximation. And here you can see it nails it pretty well. So that's what we want to do. We want to learn approximations of functions from data, which seems very abstract. But I want to point out that functions really can be anything, including things in the real world. So for instance, you interact with everyday services like Facebook or Google. Behind the scenes there's a function that we are trying to compute that's predicting whether or not you're going to click on either an ad or a piece of newsfeed content. And that is really a function where the inputs are all the things we know about you and what you like, et cetera. And the output is the probability that you click on that piece of content. Object detection. This is one of the things that we can do now. We can look at a scene, for instance, this one, and we can say, oh, this is an auditorium. This is a person sitting. These are slides. This is a computer. That type of thing. And so for object detection, this is the same type of function. The inputs are all of the pixels that I might have in a photo of this room, and the output would be the label for the image. Q&A. You've seen a lot of text bots, a lot of things that encourage you to make dialogue with AI agents. These are also functions. The inputs are the sequence of things that you've said to the bot, perhaps some history and context about who you are. And the output would be the answer to the question that you asked. And then finally, if I really wanted to really take this to the extreme, life is a function. You know, all of the inputs to all of my senses up until now are the inputs, and the outputs are the signals that I send to my hands and to my voice and the things that I choose to do. So you really can think of anything where you have to make a decision and inputs come in and outputs go out as a function. And so we can apply machine learning to all of these more human problems as well. And what's happened in the past couple of years is exactly what I described before, happening much faster. So nowadays we have more data because we all live our lives online, and we have services like Facebook and Google and all the other things that we use that can accumulate all of this human data about people that we can analyze. So we have more data to build our approximations. We have faster training. Technology has improved. The software and hardware that we use to do the computation that makes us train these models is much better than it was just a couple years ago. And we have more powerful models. Neural networks, something that I'll give you kind of a brief overview about them, are capable of learning all types of really complicated functions. They can make use of lots of data, and they're really showing a lot of impressive results. So you put those things together, and what you get are capabilities that we can explore with computers that we couldn't just a few years ago. So let's dive in. What is a neural network? What does that mean? Well, it's actually not that complicated, and I'm going to jump into it. Here, in this figure, you can see on A, that is a typical neuron in the brain. A typical brain will have about 100 billion of these all wired up and interconnected. And you can see on the left, it has this cell structure, and it has these things called dendrites. And the dendrites can be stimulated. That's when they receive signals, they get a little excited. And they come together, and if all the dendrites, if the sum of the stimulation on that neuron exceeds some threshold value, then you'll have an electrical impulse travels along the right side of this neuron, down the axon, and out the end of a neuron. And that's what we call a neuron firing. And so in figure B, we have the artificial version of this, the thing that we might use in a computer. And it has the same structure. It has these inputs, X, which you can think of as kind of the stimulation on the dendrites of the biological neuron. They come together, and there's some activation function, F, where if all of the inputs to the neuron exceed some threshold, then an output comes out the side, Y. And these have been, artificial neurons like this have been explored for a long time. And it's only recently that we're able to make use of them and train them to do interesting things. In figure C, you see that these neurons can be interconnected. In your brain, all of the neurons can be wired up to all of the other neurons. And while there are about 100 billion neurons themselves, these points where one neuron is connected to another, there are something like 100 trillion of those in the brain. So the points at which things can connect, these things called synapses that really kind of encode who you are and how the brain works, there's a lot of them in a human brain. But we can do the same thing for artificial neurons. We can wire them up so they stack on top of each other. The output of one becomes the input to another. And we have the same sort of analog to synapses in the computer. And this is an artificial neural network. And this is the sort of relatively simple explanation, but the artificial neural network is kind of the key workhorse behind all of the things that you hear about, all the advances in AI that you'll hear about today and in the press and in the media. So hopefully that makes sense. Let's talk about some things that you can do with this type of technology. The first general domain is in visual perception. And so that's something we take for granted. We can look at a scene and we immediately understand what's going on. But computers have struggled with this. In fact, we are so sure that computers can't do visual perception tasks that we use them to make sure that you're not a robot. If you've ever filled out one of these CAPTCHAs, that's exactly the concept here, is that the computer can't read the image. And in fact, yesterday, if you came to the talk, the CAPTCHA project was my undergraduate research, and my undergraduate research advisor was Luis von Ahn, who gave, I believe, the keynote yesterday. So good continuity in the programming here. So traditionally, the way you would have solved a problem like this is you would have built these things called feature extractors. You would have tried to figure out, well, maybe we can detect some edges in the image. Maybe we could figure out what cars look like. Maybe we could detect a circle and then figure out if there's a rectangle on top of it. And maybe that would be a good signal that then we use some machine learning. We do some sort of classifier on top of that. And maybe we can figure out if this is a car or not. That's the sort of traditional technique. These days, with neural networks, what we do is we feed every pixel of the image in, and we use a stack of these neural network sort of models on top of each other. And then only at the end, we get a label, and we train everything end to end, which sounds sort of vague. But I'll give you an example of how it works. This is sort of some internet archaeology. This is one of the first convolutional neural networks. This is being used to do handwriting recognition. And there was a time in the 1990s or 1980s where this network, the first convolutional neural network, was reading about 50% of all the checks written in the US. So this was one of the first applications of this technology, detecting handwriting and printed digits pretty well. And you can see the man operating this computer a very long time ago is Jan LeCun, who was my co-director at Facebook AI Research. So to give you a sense of the structure of this network and how it works, it's looking at this image, and it's applying filters over it. So it's got these filters that look for patterns, and it tracks where those patterns appear in the image and then creates some new images that represent those. And then it passes some filters over those and so on and so forth until it's whittled the image down to a small set of factors that it can then make a decision about. Here's a visualization of how it works. So in the middle, you have the input image. On the left column, you see the output of the first set of filters, and you can see they're doing relatively basic things. They're sort of looking at edges and contrast. You can see the output in the second column of the second set of images. You can see things are getting a bit more abstract. The network is sort of processing its input a little bit more. In the third set of images, you have the outputs of the final layer, and those are pretty indecipherable. You can't really tell what the network is learning there. And then finally, you have the prediction. So basically, the network is doing some very basic visual processing, building some abstract layers on top of that, and so on and so forth until it learns end-to-end, from top to bottom, how to build a model of turning the pixels in this image into the number that it represents. So don't worry if you don't follow all of that. It's not that important that you understand. I just thought it was useful to go into the technical details here. And what we do now is we can do the same type of thing. If you saw the old computer in that video, it was quite out of date. These days, we do this type of work on things like this. This is one of the Big Sur servers that we developed at Facebook. It has 8 GPUs, all from NVIDIA. And to give you a sense, Deep Blue, which was the supercomputer that beat Garry Kasparov in chess so famously, that was a 96 gigaflop machine. This is a 56,000 gigaflop machine, so roughly 1,000 times faster than the supercomputers that dominated not too long ago. So visual perception is something we can do, and we have lots of applications for this. So you're all familiar with facial recognition. This is powered by neural networks. We can tell who people are. In fact, the state of the art in face recognition these days is far, far beyond what we would consider human performance. We can also, there we go. We can also label images. So in the top, this is just a stream of images coming into Facebook servers. At the top are all the ones that contain fireworks. Actually, these are videos. In the middle are all the ones that are labeled with food and are about food. And on the bottom are all the ones of cats, because you cannot talk about the internet without somehow mentioning cats. It seems to be the rule. We also can do things like this. So this is plugging in all of the pixels of an image and then asking the network to label each pixel with what it is of. And this might be useful if you wanted to teach a car to drive. So here you can see it can label which parts of the image are the road, which parts are other vehicles, which parts are pedestrians, buildings, sky, that type of thing. And this type of technology is literally running, if you are lucky enough to own a Tesla, there's a small chip that is running basically this type of network whenever you turn on autopilot. We also have gone beyond being able to label just one image and what it's of to being able to label individual objects and actually segment them. This is from a pretty recent competition from MSR and a couple of other places called COCO. And it requires a neural network label all of the objects in the image and provide these little sort of coloring ins of the image. And this is something that was, again, not even close to possible just 2 years ago, and now is kind of the cutting edge, and we're seeing close to human performance on this type of task as well. And then I saw, actually, this was just a couple weeks ago, I saw on Hacker News, this was a network someone threw together. They pulled some code off of GitHub that inputs black and white images and then learns how to color them in. So here you can see on the left, you have black and white images. On the right, you have the actual colored images that they started from. And then in the middle is the guess that the network provided. And you can see it learns some pretty interesting things. It learns that skies are blue. It learns that grass is green, water is blue. It kind of learns this like vague tone for human skin. I'm not totally sure why, but even something like this is something that people are doing sort of in their spare time, and again, wouldn't have been possible just a couple years ago. So that's all in the domain of visual understanding. Let's talk about language, or what I usually call symbolic understanding. And to do that, I'm going to need to complicate our model for neural networks a little bit. On the left here, we have a traditional neural network. This is really simple. You have some neurons. Their inputs flow up to this second layer of neurons, and then so on and so forth through these 3 layers. Pretty straightforward. On the right, we introduce this squiggly concept here, this idea that the output of one neuron is going to flow back into itself. And what that means is that when we run this network, the second time that we run it, we will include in the inputs for that node in the middle the previous output of that node as one of the inputs for the next run. So that basically means the previous run, some of the state from the previous run is getting fed back in and some of the context is being preserved across runs for this network. And this turns out to be hugely, hugely important and powerful. Brains themselves are mostly these sort of recurrent connections where things go backwards in the network instead of forward. And one really interesting way of thinking about this is that in a traditional network, you're learning a function. You have some inputs, and they go through the network, and then you get some prediction of the outputs. But with a recurrent network, because this state is preserved, we can learn all types of full programs. So the dialogue agent that I talked about in the past, a good thing to do might be to preserve some of the state throughout the dialogue, so I know that when you use prepositions, who you're referring to, or if we have a dialogue about booking a venue, I don't have to ask you the details of it every time over and over. So you can see we can learn all types of functions that are really full programs and preserve state across different things. This turns out to be really important in language because even just a simple sentence can have all types of crazy structure that's, sort of not quite as straightforward as we usually think about it. Even a sentence like this, if we try to parse this one sentence, you can see all the interrelationships between adjectives and verbs and subjects and nouns. You get this pretty complicated tree. And so learning a program that can input a sentence, remember some of the state in the past, and really understand it is one of the advances that we have in AI these days. So here's a couple demos of this technology. First, this is my favorite. This is a network that was trained to learn this pattern of its inputs on Shakespearean text. And then we can turn the network over and we can make it generate completely synthetic Shakespeare, and this is what it comes up with. Actually pretty convincing Shakespeare, I would say. It even gets the different characters, it gets the tense, it's roughly getting iambic pentameter, pretty impressive stuff. We did the same thing, training a network on a corpus of text and then having it generate synthetic examples of it on Facebook posts, and we got much funnier results. So here's a bunch of random Facebook posts completely synthetically generated. You can see it understands some things. It gets some of the structure, but it really doesn't understand the world quite as well. My favorite is I have an urgent Candy Crush exam, which is not something that people would. But you can see it really understands, that urgent is about exam, and Candy Crush is something people do in class, but it doesn't quite understand why those might not work together. And so we. Working toward dialogue systems, this idea that we can all interact with chatbots and stuff is something we spent a lot of time working on. Here's a system that uses recurrent networks to read a story, in this case, a relatively much simplified version of The Lord of the Rings. If you haven't seen The Lord of the Rings or read the books, avert your eyes because there are spoilers involved here. But the network can then take questions and answer remember the context from the text that it read and then answer questions about it. So this is something we call baby text. And then finally, sort of combining the stuff that we learned in visual perception and combining that with this symbolic understanding, we can build these networks that on one side process the pixels, but then go through one of these language generation networks and kind of staple these two techniques together. And we can plug in pixels and generate captions for text. So you can see this is actually trained on what people might actually caption this photo with. This is actually quite good. This photo, the caption here is a group of people standing, shopping at an outdoor market. There are many vegetables at the fruit stands. Pretty convincing. And of course, this is something that we deployed to make it a little bit easier for our blind users to understand the stuff that was scrolling through a newsfeed. So if this, not sure why it's not playing, but this is a demo of a blind user being able to understand everything that's going on their newsfeed, whereas in the past they couldn't see any of the photos. So the final thing that I want to talk about is a little more abstract. It's about learning representations, and this is something that we call embedding, which is actually a little complicated to describe, but is actually really fundamental to how human beings understand the world. And it's important to realize that we don't remember every pixel of the world that we see, right? We don't remember every detail, but we do remember high-level themes. So we remember representations in our brain. Somewhere in there is stored the faces of our friends and the fact that some of our friends, like playing chess and some of them don't. You know, all these sort of higher order memories are stored. So how can we generate these higher order memories? How can we generate a representation from the world that's compact and a summary of the things that we want, but is also useful? And so that's what this technique that I'm going to talk about, embedding, lets us do. It lets us take high-dimensional stuff, like a photo of this entire room, and then create a mapping where we can move that into a different space where it's smaller, but also has a bunch of useful structure in it that we can use to make decisions in the past. So, and we can do that because we can use connection and similarity. We understand, we have enough data to tell us which things are similar and which things are separate, so we can use that as training for our model. So it's very abstract, hard to understand. Here is an embedding model built on Instagram photos. And this uses its knowledge of what Instagram photos are more similar to then train a visual network to understand what's in photos, and then uses that to group photos that are similar together in ways that we couldn't do in the past. So here, this is in the embedding model, this is the sort of kitten region. Down here, you can see it's grouping all the dogs and the puppies together. And then now, if you visualize over here, it's all the things that are food together, even if they don't quite look the same. It understands the difference between different types of food. This is the sort of flower region, et cetera. Things like that. So this is kind of grouping things together and exploring what things are similar and what things should be grouped together, more in the way we would think about it than in the way a computer might traditionally think about it. And so we can do the same thing for words. This is a very common model that you can play around with, very easy to run, called Word2Vec. And what it does is it builds these representations that I talked about. It builds that sort of embedding space before out of words. So here you can see that if we plug in, this is if we plug in these are all the most similar words to Sweden. And you can see it understands Norway, Denmark, and Finland. It's all the countries that are similar to Sweden. But it also understands all of this other structure. So here, if we train the exact same model in English, and then we train it on Spanish, and then we map out where the words end up, you can see that on the left is a map of where the words end up in English, and on the right in Spanish, and you can see the structures are roughly the same. It sort of understands that the relationship between 1, 2, 3, 4, and 5 is the same in both of these languages, and the relationship between cat, horse, cow, pig, dog is the same in both languages. And it even gets all these more interesting relationships. So you can ask it to do these sort of word associations, just like you might see on the SAT, or for those of you that are from the States. So if you ask it, king is to queen, as man is to, it gets woman. So it understands these sort of gender relationships. China is to Taiwan, as Russia is to Ukraine. It understands these sort of geopolitical tensions. Knee is to leg, as elbow is to forearm. It's pretty good at anatomy as well. And even crazy things, Donald Trump is to Republican, as Barack Obama is to Democrat. You know, it understands current events and things like that. Just from feeding it a corpus of text and asking it to build these representations, we've captured all of this structure of language that we use. And we can do the same thing for images. So this is a network that builds these representations of images and then creates completely synthetic images out of the space that it generates. So here, these are different completely fictional bedrooms at relatively low resolution. But you can see they're pretty plausible images that would confuse a person about whether or not they were bedrooms. This is the same thing to prove that they're synthetic. This is smoothly walking from one bedroom to another, and at each point generating a new synthetic bedroom. And you can see the windows morph into beds and doors and televisions and things like that. So it really is sort of understanding what makes a bedroom a bedroom. And then some even more interesting stuff, just as we can do arithmetic on these representations we learned of words, we can do the same for faces. So these are synthetic faces. On the left are a bunch of faces of men wearing glasses. We take the inputs that generate those and we average them. In the middle are a bunch of inputs of men without wearing glasses, so we take the inputs there and average them. We subtract them and then add in this vector that represents women without glasses, and sure enough, it puts you right in the space, right in the area of the space that is images of women that are wearing glasses. So there's all types of structure that these spaces can understand about the world that's sort of more similar to the way we might understand things than storing things as raw pixels. And then finally, I thought there were some fun applications of this. This is totally synthetic manga characters from anime series. These are totally synthetic. This is one of my favorites. These are totally synthetic album covers. So if you have a band and you don't feel like designing an album cover, talk to me after the talk. We can make one up for you. And just all types of things that we can now generate because we understand the space, the sort of semantic space that things might fit in the same way that people do. We can ask computers to do all types of things. So that's about it. I want to leave you with the final point. If you had to learn one thing today, what would you learn? Well, it's that these days, there's a lot more data in the world that represents how humans understand the world. We have faster training because we've evolved the software. We have really fancy hardware. We have all types of things that let us train on humongous amounts of data in relatively short amounts of time. And we have these powerful models that are mostly empowered by advances in neural networks we understand and we're able to bring to bear. And so with that, with these three things, there are many new things that we can do now that we could not do 5 years ago. So thank you, Berlin.